Yeah, sure. Now you can see my screen?
Not yet. Yes, now it's loading. Yes. Okay. Now we can see.
No, something happened. Okay. Good afternoon to everybody. First of all, I would like to thank you to give me this opportunity to give this talk. Today I'm going to speak about some kind of representation of exterior powers, which is a part of what I did along my PhD thesis, but more simplified cases. I start with some preliminaries, a kind of prologue. And first of all, I would like to remember you since the days of Arthur Cayley. All of us knows that how we can multiply a matrix by a vector. For sake of provocation, I put here this very simple example. To take this matrix, to take vector xy, and we know how we multiply and then obtain this vector. You see, it's so simple, but just a minute. It's so practical as well. And this product has further property, which I'm going to explain more about it. Consider a field K. We know that a dimensional vector space Kn is a module over K-valued n times n square matrices. For this module structure, you just use the product of a vector and a matrix. But we know that n times n square matrices is a Lie algebra with respect to the usual commutator. By commutator, I mean the commutator of two matrices, n times n square matrices, n1 and n2 is just n1, n2, subtracting n2, n1. And the model structure of Kn over Kn times n square matrices has this property, which is compatible with the Lie algebra structure. By this, I mean, if you take two n times n square matrices, n1 and n2, and the vector u, you first multiply n2 by u, and the result you multiply by n1, and then you subtract the multiplication in the reverse order. What you get is exactly the commutator of n1, n2 by u for any n1, n2, and any vector u. Okay, let me go a little bit in historical part of our work, which kind of invitation is for us. For Japanese mathematicians, they invoke Kashiwara and Miwa, which we abbreviate their name by the acronym DJKM along our discussion. In 18, working on a completely different subject, realized that the polynomial ring in infinitely many indeterminate, which is called the bosonic box space, is a representation of the Lie algebra, but which Lie algebra? The Lie algebra, which is denoted by GL into the Q, which is the vector space of all infinite size matrices, which all integers of them are 0, but finitely many. So for this module structure, they should have a recipe. The recipe is like this. You should have a matrix, you should have a polynomial, and you multiply and you obtain another polynomial again in such a way that B turns to be a module over GL into Q. So what they did is like so. they proved in this very famous cited paper that I think one slide here. There is one missed slide here, but they consider the vector space having they consider vector space having a basis parameterized by integers, which is the universal model of it is just a vector space of Laurent polynomials. I cannot show here to you because there is a mistake. I'm so sorry. But in the sequel, I think there is a related slide that you can see what I am doing. And the dual basis V star, which has delta J's as dual basis of Xi's. So we have the Kronecker delta, and if you consider, just a minute, maybe. Yes, there is a repetition and there is a mistake here. ECW minus 1 is a generating function of basis elements of GL inf TQ. And they should know how it acts on a typical element of P, say Px. And they prove in this cited paper that if you act by EZW minus 1 on Px, what you get is this nice expression. And mind that this two-part exponential, which is have to do with theoretical physics in fact, is denoted by gamma ZW and is what people call it as vertex operator. And with this action, the bosonic Fock space turned to be a module over the GL inf TQ. So now I'm going to give you a feeling to understand what is going on. In fact, what I mentioned you at the beginning of this talk, the representation of Kn as the n times n k-valued matrices is completely related with what Kashiwara-Miwa did, and you can find more detail about this relation in this cited paper by Gatto and Salehian. During my PhD thesis, I tried to put more pieces in this picture, and in fact, I studied exterior algebra of a vector space as a representation of the Lie algebra with endomorphism, which for sure includes all the previous cases. I mean, the ordinary matrix multiplication, the Kashiwara-Miwa representation, and all the results by Gatto and Salehian, and even more results. But now I'm not going to speak about all what I did because of the lack of the time, but a piece of work and the simplified version of this. Now, consider n-dimensional vector space Vn. You know that we can write it as a quotient of polynomial ring modulo xn. And in this way, V inf t, which will denote it by V, is Qx. Okay, but for the time being, forget V x1, x2 with inf t indeterminate. We are focusing on Vn, which is a n-dimensional vector space, a finite dimensional line. You know very well that it has a natural basis, which is this x0, which is this column matrices, having 1 in the first entries, and all the other are 0. then x1, which has 1 in the second row, and other integers are 0, etc. And xn minus 1 is having 1 in the last entries, and all the others are 0. Now consider the dual basis, which denoted by dj. X0 is this. Similarly, delta 0 is this, delta 1 is 1, 0, 1, 0, etc. And delta minus 1 is 0, 0, and the last entry is 1. Okay, so you can see easily here that delta j xj is just matrix multiplication. So you have that just Kronecker delta. It's just a scalar. Now consider the Lie algebra G, which is GLVN. You can see here what they did, GLVN is defined Vn tensor Vn star, and since we are in finite dimensional, it's exactly q-valued n times n square matrices. So it has Vn tensor Vn star has xi tensor delta j as its basis. And now let me give an example to be more clear to you. E1, 2 by definition is x1 tensor delta 2, which is precisely these 3 by 3 matrices. And we can write any 3 by 3 matrices, of course, as a linear combination of xi tensor delta j. Okay, now this is a very simple but important observation, which is this: any vector space V is a GLV module, but and the module structure is like this. You take a matrix, you take a vector, and you define the module structure. The product to be multiplication of a matrix by a vector. And it is so simple, but very important. Now let's play a little bit more with combinatorics. By generating function, I mean this. You consider xi tensor delta j, which is a basis element of GLV. Then you add 2 more indeterminate CIW minus j, and you sum all of them. We write it as ECW minus 1, and we call it generating function. The action of generating function of GLV on V is determined when you can determine it on a physical basis element of V, like xk. So ECW minus 1 xk by definition is this xi tensor delta j CIW minus 1 xk, which is the summation of xi delta j xk CIW minus j, and you know that delta j xk is Kronecker delta jk, which vanishes for all j, but when j is equal to k. So we have this equation w minus k sigma xi zi. This last part is very important. For the time being, we'll just denote it by some notation in the sequel, and I will mention later. But what is this equation saying? Is say that the image of xk through the endomorphism xi tensor delta j is the coefficient of CIW minus j in the right hand side.
Excuse me, Somaye.
Yes.
Somaye, there is a Letterio that wants to ask a question. So he sent a message in the chat. I don't know if his microphone. So if Letterio, if you have a question and you can hear me, and so either you can ask, or otherwise write in the chat. No, we can't hear you. So maybe you can just write in the chat. So maybe just check if your microphone is connected. Yes, so we can't hear you, Letterio. Yes, maybe we continue the seminar, then by the end, maybe you will fix your problems and you can ask directly the question. Okay, so Maya, so you can continue, so I'm sorry.
No. So, yeah. And whenever J is different from K, the image is just 0. Okay. But we can write the expression more elegant. As I mentioned you, the last summation, this, if you can see my phone, sigma xi zi is what we denoted by sigma plus zx0. For the time being, it's just a notation, but for us allowing the details is a very important tool and called the Schubert derivation, which is a summation of sigma zi's, which acts on a basis element xj just as the shift operator. Sigma xj is just xj plus I. But for the time being, it's just a notation. Okay, and so even we have compact this formula more by adding one more in a variable t and sum again the relation sigma zw minus 1 xk and tk that we added right now. Now we have this sigma ECW minus 1 xk tk is equal to, but by the notation I explained you, sigma plus dx0 multiplied by this summation. Sigma tk over wk is a geometrical progression, so we have this relation times sigma plus z.
Do you hear me?
Now I hear you,
Yes.
Letterio, yes.
Yeah, I think that probably you want to write that k is from 0 to n minus 1.
Exactly. We are in the finite dimensional.
Yeah, but you in the second sum you missed. There is.
Let me see.
No. In that slide.
Where you are
No. In the
speaking
slide
here?
where you were. Go.
Mm-hmm.
Yeah, the
Here.
second. Yeah, you see
Yes,
the second.
exactly. Yeah. The geometric progression, as you see, I didn't write as 1 over 1 minus t over w. I'm writing 1 minus tn over wn. Quotient 1 minus t over w is because it is finite sum from from k equal to 0 up to n minus 1. Okay. Enter. We have enters in this sum. Hello.
Okay. Yes. Okay.
Yeah. Okay. Then multiply by sigma plus cx0. And now observe that this summation, which is 1 minus un over 1 minus u, we want to write more elegant. Since 1 over 1 minus u, we can write in this exponential form. So we have this equation, and the last part is now sigma minus ln 1 minus u. And then we can write it as integral of du over 1 minus u again. And this is 1 over 1 minus u we can write again as this summation 1 plus u2, etc. And then we take the integral. What we have is this u plus u2 over 2, u3 over 3, and so on. And sorry, you can summarize this parenthesis by this summation. And now, instead of u, you just put T over W in the formula 3. What we get is this. Sigma easy W minus 1 xk tk is equal to, you see that instead of u, we put here T over W. So we have 1 minus Tn over Wn multiplied by this exponential and times sigma plus Cx0. And mind that the first part, 1 minus T on over Wn, can be written in exponential form, and then we compact these two exponential in a one expression, and we have this formula for times sigma plus Cx0, which is exactly the Beijing-Boccaccio-Miwa for one indeterminate. Okay, now I'm going to explain you a very important observation. If V is a G module, we can say that exterior algebra of V is a G module. But how? Via the map delta from G to endomorphism of exterior algebra, which maps any element gamma from G to endomorphism of exterior algebra like delta gamma, which acts on exterior algebra by satisfying in Leibniz rule. I mean, delta gamma star U wedge V is delta gamma star U wedge V plus U wedge delta gamma star V. So as you see, it's enough. We know how delta gamma acts on W, any typical element of V, and we define delta gamma star W to be just gamma star W. This is completely defined because we know that V is a G module. So delta star V is well defined. By this delta, we see that exterior algebra is a G module as well, and this delta has further properties, which is an algebra homomorphism as well. You can easily check that delta commutator of gamma 1, gamma 2 star is the commutator of delta gamma 1 star and delta gamma 2 star. But the point is that if R is NQ vector space isomorphic with wedge RV, then R is a G module as well. So, for example, wedge 2V is isomorphic with V2, which is polynomial ring in two indeterminate E1 and 2. And since wedge 2V is a GLD module, then V2 is a GLD module. We will go on in this example more, but before that, allow me to say you what we mean by contraction. The contraction of element of R's exterior power of V, U1 wedge U2 wedge UR against delta, an element of V star, is defined through this diagram. Delta contraction with U1 up to UR is this like determinant. And when you take an element wedge RV and you apply delta, you take contraction, you feel you have fallen in wedge R minus 1. Maybe it seems a little bit difficult, but allow me to show you how it works by this simple example. Let's compute delta contraction with U1, U2, U3. By definition is this this diagram. Okay, now let's compute it. You have first delta U1, then you eliminate the first row and the first column. what you get is U2 wedge U3. Then you have minus delta U2. You eliminate first row and the second column. What you get is U1 wedge U3. And then finally, you have delta U3. You eliminate the first row and the last column. What we get is U1 wedge U2. This is what we mean by contraction, an element of exterior algebra against an element of B star. Okay. Now, consider the generating function as we had before. This is the same generating function of GLD. We can write it in this form. Xizi tensor delta J W minus J. And so we can write it in this notation by our notation. This is sigma plus Cx0 tensor delta W minus 1. Now, the action of this generating function on element U is defined like so. Sigma plus Cx0 tensor delta W minus 1 star U is defined by this. First, you contract delta W minus 1 and U, and then you are wedging with sigma plus Cx0. Now let's go on with our example. Let's take in this formula R equal. Let's work with wedge 2b. So a typical basis element of wedge 2b is x2 lambda by x2 lambda, as I wrote here, is x1 plus lambda 1 wedge x lambda 2. By definition, it is sigma plus Zx0 wedge, this parenthesis, this contraction. As I explained during the contraction part, we have this determinate, okay? And then since sigma plus C x0, mind that here we are not using just the notation. We are using the notion of Schubert derivation. Schubert derivation can, enjoying the integration by part property, we can write this, and then you can filter sigma plus bar z inside the determinate. We have this equation, and sigma plus z, sigma plus bar z, sigma minus z, and sigma minus bar z are Schubert derivation. And by definition, we have this equation as well, and then you can factorize z from the second row, and when you are wedging with x0, you can add this last column. And this is just a few technical steps here, but you can check easily. It's so easy. Then again, since sigma minus bar z is a Schubert derivation, we can factorize it and write it outside. And also we can factorize W minus 1. So we have z over W sigma plus z, sigma minus bar z, times this determinant. Now, you see here sigma plus c and sigma minus bar z. Our Schubert derivation is the first one, sigma plus c, exactly the first exponential part appearing in the DJKM representation, and sigma minus bar z is the second exponential expression. With our notation, as I explained you along this talk, then we have this main theorem in general case for wedge R lambda. When we act by generating function EZW minus 1 on X R lambda, what we get is this expression CR minus 1, WR minus 1, sigma plus C, sigma minus bar Z, multiplying by this expression. This is so simplified version of our main theorems in the thesis, but because of the time, I just put this part for showing you some part of works we did along the thesis. And I think that I could be on time, and you can find more detail about what I explained you in my PhD thesis by titled Hasselschmidt derivation and vertex operator on exterior algebra, and another papers which you can find in the reference 2, 3, 4, and other references for more detail as well. Thanks for your attention.
Yes, thank you, Samaya, for your talk. So are there any questions or remarks that you want to ask?
So maybe...
Yes.
I thought, I think that, yes, for Somaya it's easy these things, but probably she was too fast. I missed one slide. Can you give at the middle of your slides, please? Before, yeah, go ahead. Yes. Okay, now go more. Next slide. Yes, go. Okay.
This is our goals.
Go more.
And here we have finite dimension.
Yes, go more. That now go slowly. Yeah. I think, this is something I was missing. I thought it was, I mean, here you are putting E1, 2. Yes. So you are then saying that EIJ are the elementary matrices, those which have all 0 but 1 in position IJ,
right?
In
the position.
Yeah, but I think then you are missing some slide because I mean, it appears there for the first time. Go one slide before, please. Yes, okay, so that's the problem. That's why I was missed, because
about the
there should be the definition of, I mean, at least the notation EIJ, but now it's clear. So EIJ.
No, it was Letterio. You mean about introducing EIJ as XI tensor delta J, right?
Yes.
It was in a slide which I think that I removed it by accident when I was compiling for the last time before my talk. Yes, and it was the reason you couldn't see it. I'm so sorry, but it was in this slide.
I see.
Any other questions or comments?
Yes, maybe I would like to ask you just a moment if you can show again the Jimbo Kashiwara Miwa formula. I just want to understand the characters appearing that formula, or maybe it was the slide that was missing.
I think it's.
So there it appears. So from my notes that I took, yeah, maybe it was the next slide. Where so you write the yes, so this star product is so I see the generating function, and maybe if you can remind me what PX is, because probably and what is
Sorry?
Yes, what
This
is
first exponential?
PX? Yes, yes, I would like to know, because I miss PX, what it is, and the star product.
Yeah, okay. EZW minus 1 is the generating function of GL in CQ. But PX is a basis, a typical element of P, a polynomial. It's just a polynomial.
Okay. Yes.
You know? Now you can see here we have the partial derivative. You can apply it on Px and you compute this expression. Okay. And this first exponential.
Because later also there is a star product is for the representation.
You're right.
G on the exterior algebra of
exterior algebra of P. Exactly.
Yes.
This part.
Okay, yes.
May I make a comment?
Yes.
Sure, let's hear you.
Go to the date Jimbo Kashivara Miva expression. So the comment is that people may think that the exponential of that differential operator applied to a polynomial is something difficult to compute practically. But it is not, because it turns out that you can easily see that if you apply, for instance, to xk, if you apply that to the polynomial xk, is something like xk minus I mean, is just a moment. Is if I apply? Oh, let me think. It is precisely xk minus 1 over k. You can check that if you take that exponential, so you expand and you apply to xk, it gives you xk minus 1 over k. Okay? So it is very easy on the generator of the ring. The ring B is the ring in infinitely many indeterminates, x1, x2, okay? And then what makes the game easy is the fact that that exponential is a ring homomorphism. So for instance, if you want to apply that exponential to the monomial x1, x2, it's so easy. It's just x1 minus 1 over 1 times x2 minus 1 over 2, and you just multiply. This is the comment I wanted to do.
Yes, thank you, Letterio. Yes.
I mean, I wanted to make the comments more for the audience.
Yes.
It's a pity that we cannot write by Blackboard. It was more easy and people could feel the content of what I explained to them better.
Are there any other questions or comments? Well, so if there are no other questions, let's thank again Somayer for her nice talk. And well, so yes, so I hope that this talk will be also of motivation for our master students and PhD students, because as Somaya remarked, so she started working on these topics during her PhD training that she just finished a few months ago. So I hope that this will be as a motivation also for our students to do the same.
I hope so.
Okay, yes. Yes, so thank you so much again.
It was
And
a pleasure.
well, we will,
invitation.
yes, we stay in contact because through the MARM project. So
yeah.
Theorem will in touch. Yes, maybe I don't know.
Sure.
Martin was saying something. I heard.
Martin?
No,
Yes.
Yes.
Thank you so much. Keep well there.
Okay.
All right. Thank you.
Hi, Martin. I'm trying to do some work for you by tonight, okay?
Yes, I hope you saw my email. I see you're still quiet, so I'll wait for you to respond.
Okay. So
also, if there is no other question, we can stop the recording also.
Yes.